So the last couple of lectures, we've been working to solve the time-independent Schrodinger equation in spherical coordinates. So we started a couple of lectures ago in going through and trying to find solutions that are separable. So one, a function of r, which is only a function of the spherical coordinate r, and then the other function, which is a function of the angles. And so we've spent some time with the angular equation. Today we're going to look at the radial equation. And so here's the radial equation as we were left when we first separated. This is our constant. Again, it's that special constant that we're learning about a little bit more about every day, what these L's mean, but we'll continue on that path. Now, not every book does this, but some books will rewrite this equation in terms of a new function r, which just ends up making this a little bit simpler. And so if we just drop the as a function of, then our big R will be u divided by r. And so what we can do is go through and just simplify this a little bit. It's really just about cleaning it up. It's not even an essential thing to do. So if I write d big R with respect to r, then what I'm doing is I'm taking the first derivative of the function u divided by the variable r. And so make sure you follow me here. But if I go through, there'll be a product rule here for this particular, and then you can write this in an especially nice way, 1 over r squared r du dr minus u. And why did I write it that way? Well, because we know that we're going to plug this first derivative in right over here, and there's a factor of r squared. So this r squared here will cancel with this factor of r squared on the bottom here. And so if I want to rewrite this equation, I can just say d dr, and inside here I'm just going to have only these pieces, r derivative of u with respect to r minus u. And if I go through and actually find this derivative, so there'll be again a product rule with these two guys, where I get these two terms here. And then lo and behold, I get a negative du dr. And so these two pieces cancel. And so this is basically the reason that we do this. It just makes this much simpler. And so if I rewrite this equation, all right, so this whole term here is just this piece, r second derivative with respect to this new function u, and then I just write in the rest of this equation here. Again, this is for any central potential, so we still haven't done this for any particular potential yet, which is nice. Be careful. And so here, so this is our functions of r, and again what we're doing here is we're going to replace these functions of r. So I'm going to replace these with this u divided by r. And when I do this, I'm able to rewrite this equation as such. Excuse me. And so what I'm going to do is I'm going to bring this piece over here. Okay, so make sure you go through this algebra and see where we're getting this from. When we write it this way, all right, this looks very similar to our one-dimensional time-independent Schrodinger equation we were using previously. It's just that now you can sort of call everything that's in this parentheses v effective. So you can think about this whole term here as being sort of one term. But if you do that, then you've got this part here, the second derivative of our function, the potential times your function equals the energy times your function. So this will just be helpful for cleaning this up a little bit. All right, so we're going to try to solve this equation. So this is our radial equation where we've plugged in for our potential, the potential of the hydrogen atom, the Coulomb potential. So again, the idea here is that we have the positive proton at the center of our system, at the origin, and that vector r points to the location of the electron. And so for our potential, we have this here. And so our goal is to go through and solve this differential equation. So we're going to spend some time just trying to make it as simple and as compact as possible. So the first thing I'm going to do is just multiply both sides by this constant, negative 2me over h bar squared. Now, just be real careful that m sub e is the mass of the electron. We're just trying to be careful because there are different m's floating around at this point. And so here, this will just leave this second derivative here. And then inside here, so the negative sign will cancel. We'll get me over e squared. And then a factor of 2 cancels with this factor of 2. So 2 pi epsilon naught h bar squared, and I'll write this as 1 over r just to keep things a little neater. And then here, when I multiply by the negative constant, I'm going to incur a negative sign, but the constant will all cancel out, so this term gets a little bit nicer, times u. And then over here, I'm going to have negative 2me times the energy over h bar squared. So we're going to make two substitutions. We're going to call kappa equal to something looking like this over here. And our second substitution is rho is equal to kappa times r. And again, the idea here is just to make this equation look as simple and as clean as possible. And so here I'm basically going to take these constants over here Alright, and so let's think about how each term will be affected by this. So the first thing is we got to look at how are we affected taking the derivative with respect to r. Okay, so if I do something like this, I can write this out to get a sense of how this works. So these two d rhos will cancel, and so I can get this factor here, and so d rho dr just from this equation here will give me a factor of kappa. So it's kappa d rho. So we can first transfer this double derivative, so I'll end up with a kappa squared term, d squared u d rho squared. Now here, this thing looks almost like this, except there's an extra kappa. So what I'm going to do, I'm going to multiply a kappa on the bottom, and then a kappa, so basically a kappa over kappa, so multiplying by 1, and it just makes this thing equal to that new constant. So again, we're just trying to clean everything up. And this gives me kappa over r. This guy here just got cleaned up, isn't really affected by anything right now. And then this over here, this will equal to kappa squared by u, because that's sort of the definition. So these two definitions were meant to clear this up and clear this up a little bit. Now the last thing I would do in cleaning this up is divide everything by kappa squared. So each term I'm going to divide by a kappa squared, which of course is going to clean up a lot of things. So I'll get this d squared u d rho squared. Now this one over here will be rho over kappa times r once I cancel things out. This is negative L over L plus 1 over kappa squared r squared. And then this will be just equal to u. And so you hopefully can see here that what I can do is replace this with a rho, and then reduce this piece over here with a rho squared. So I've got everything about as clean as I possibly can. And so a nice way to write this equation, you're just sort of finishing up here, would be like so. So put everything on the other side. So we got a factor of 1 from this guy, minus rho over rho naught from this term, and then plus L over L plus 1. And so this is sort of our final equation, the final form that we're going to take and try to get the solution to this here. All right, so our goal is to find the function u as a function of rho of this equation, at what point this will be our solution to the radial equation for the hydrogen atom. Now we're going to go through what we call the power series method, or the method of Frobenius. So you can look this up. I definitely advise you to look this up and see how some people approach this stuff, especially if you're more interested in some of the math that we're doing. So the first step generally for this is to look at the asymptotic behavior of your equation. And so if you look here, when rho is really, really big, okay, so if you look here in these equations, when rho is really, really big, both this guy and this guy are going to go to 0. And so our equation, we can write it approximately like this here. So the second derivative of u with respect to rho equals u. This is a differential equation where the solution, and you can go through and check this. Our general solution would be this here, exponentials. Now, so here's the thing, and this is going to be something we're going to talk about, throughout this calculation, is that the differential equation doesn't really know, what we're trying to do with it, and so it'll oftentimes give us solutions that aren't helpful. In quantum mechanics, we always want solutions that go to zero at large, or that don't blow up, basically. And so right here, we don't want this piece here. And so we can say that the asymptotic behavior at large rho, okay, we want our equation to look something kind of like this here. Now we can also look and see what happens as rho goes to zero. I should make this look more rho-like. So in that case, right, if we look at our equation, when rho goes to zero, what's going to happen is these two pieces are going to blow up, and in fact this one's going to blow up really much faster. And so our version of the equation there will look something like this here, in a similar fashion. Now here, this is a little bit more of a complicated differential equation. You can literally just plug in this solution if you want, but this is what our solution would look like. And again, we want things that don't blow up, and so when rho goes to zero, this piece here is going to be blowing up, and so our solution should look something like this here. And so what we do then is we say, okay, well, I want my function here to look something like this, and so we call it peeling off the asymptotic behavior. And so these are the two pieces, or the asymptotic behavior, and then there's some other function. And the goal here is just to make our equation a little bit simpler when we're actually looking for that particular function. All right, so here's our equation we're trying to solve, and here's the form that we're going to plug into it. And so, of course, these things depend on rho, and so we can go through and set up our derivatives here. Definitely go through this and make sure that you follow this, but it's just a lot of calculus. And when I'm done with this myself, I end up with an equation like this here. And so this is an equation of that function v. And so what's nice is that we made things that may not seem like it, but a little bit simpler by isolating this part of the function. So we're trying to solve for this v sub p here. All right, so this is our differential equation, and the method we're going to use is the power series method. And it's basically, we're going to assume that our solution can be written as a power series in rho. And so we'll just make up some power series here, and so it's our job to go through and determine these coefficients. And with our differential equation here, what we want to do is just go through and determine what our derivatives look like, but these are pretty easy. I'm just going to forget about that. We're assuming that these sums go from 0 to infinity, but I'll just drop those just to make everything look a little bit cleaner. And so this is our derivative, first derivative of that function v, and then our second derivative will bring us in something along these lines here. And what we do now is we plug everything in over here. Now, we should say, so we're going to go through this method. Again, I encourage you to look up this online and find out as much as you can about this. It doesn't work for all equations, but luckily, most of the big physics equations, this will be a useful technique. So if I just plug in, again, this is the second derivative I'll have for this piece over here. So it's j minus 1, cj rho j to the minus 2 power. And then we're just going to, again, go through and plug all these things in here that we have. So the sum of j, cj rho to the j minus 1, and then our last term over here, like so. I'm going to clean this up by, so I'm going to multiply this row all the way through, so this sum will end up being rho to the j minus 1. Now over here, I'm going to sort of try to keep together like terms of rho. So the 2l plus 1 will be multiplied by the sum of j, cj rho to the j minus 1. And then when I multiply the term of 2 times negative rho in there, I'm going to get negative 2, this sum, j, cj, rho to the j. So that rho will make this on the order of rho to the j. Then I have plus rho naught minus 2 L plus 1 Now the way this works is, so I have this equation here, and what should happen is all the coefficients for each term of rho, for each different level of rho should equal 0. So if I look here, in my sum I've got the rho to the j minus 1 here and rho to the j. And so what I'm going to do is I'm going to say that the rho to the j term should always cancel. So it's easy to write these over here. So for the rho to the j term here, I can write negative 2j cj. Again, that's the rho to the jth term. And then over here, plus rho naught minus 2 L plus 1 cj. And then for these guys, it's a little bit trickier because I want the rho to the jth term. So since it's j minus 1, what I can do is just sort of plug in for these two terms, j is equal to j plus 1. And I'll give us the term that we want. And so when I do that, I get j plus 1 times j, c to the j plus 1. So I just literally plugged all j plus 1s into here, and this gives me rho to the j. So it's the same level of that polynomial as the rest. And then over here I get 2L plus 1. Again, I'm plugging in j plus 1 into those pieces here. And so what should happen is that this equation should add up to be 0. So here is the relationship for the rho to the jth subterms. And so all this should add up and equal to 0. And so what we can do is build this relationship here, which tells us, relates the j plus 1th c term to the jth term. So if I just go like this here, this is just literally taking this equation and solving it for c to the j plus 1. And if I clean that up a little bit, it comes out looking sort of like this. Now, your first time doing something like this, you're probably thinking, well, what the heck did I do this for? But essentially, this relationship is the same thing as solving the differential equation, right? So we're looking for a solution to v of p that's a sum of the j terms and then multiplied by p to some power. And so basically, once we know C0, I can plug in C0, find C1, find C2, and go on from there. And so I can essentially find this sum. And so this is a method of finding the solution to this. Now, let's just look at our particular case here. In quantum mechanics, all right, we want only special functions. And so let's look at this thing for large j. So for large j, and that's where I can basically go into here and get rid of anything that's not j, because j is going to be super big. And so I'll end up with 2j on top, and then down here j and the j plus 1. Now you could get rid of this 1 here, but it's going to come out that'll just help us recognize something a little bit better. And so I'll keep it there. And so this ends up being 2 over j plus 1. So once j is really big, this is how these two terms are going to connect to each other. And so let's just look at, say I've got some, if you look at this, imagine, so C1 times C0. So if I plug C0 into here, then C1 would be j of 0, and so I'd get 2 over 1 C0. If I looked for C2, I'd go back over there, and for C2, so it'd be 1 plus 1, and so it'd be 2 over 2 C1, which when I plug in these guys would be 2 times 2 divided by 2 times 1 C0. And then for C3, if I plug into that, it's 2 over 3. We're just adding a 1 each time. C2. But now if I plug in my thing for C2, I get 2 times 2 times 2 times 3 times 2 times 1. And so we notice that what happens here is that the C to the J1 term for these really big ones works out to be 2 to the J power over J factorial times C0. And if we plug that in to our sums, okay, so we have 2 to the J power over J factorial rho to the J. You can write this as C0, and this is essentially the power series for an exponential function. So it's 2 times rho to the jth power. And so this is the same thing as C0e to the 2 times rho. And so if we go back to our equation, right, so equation u of rho, we have rho to the L plus 1, e to the negative rho, and our new function, the v function. Well, if that function is e to the 2 rho, then we get a situation like this here, where again this is blowing up. So this is the situation like we were talking about before. So this differential equation doesn't know that we're trying to do quantum mechanics, so it gives us all the solutions that are possible. But we don't want this solution because it blows up. We want something that we can normalize. And so what that means is that this sum is going to have to terminate. So let's talk about how to do that. So in practice, for the sum to terminate, what that means is we want the numerator at some point to equal 0. If the numerator equals 0, then some c term will then be 0, and since the next c term depends on that one, it'll end up being 0. And so what we want is, we want some situation where c capital N minus 1 is not equal to 0, but c capital N is equal to 0. And so we'd want some sort of situation where, okay, so Cn equals, I won't even care about the downstairs, but up here, we want this piece. So so if this is n, then this would be n minus 1 in here for the j, plus L plus 1 minus rho sub naught times Cn minus 1. So this one's not 0, this one is, and so that means we want this top piece here, so 2n minus 1 plus 0 plus 1 minus rho naught, we want that to equal 0. So these 1's cancel, and we get 2 capital N plus L is equal to rho. And so what we typically do is we call the capital N plus L equal to lowercase n. So 2n is equal to rho sub naught. And it's subtle, but this is basically going to set into motion how we can solve everything. Alright, so let's see where this gets us. So we just found this relationship that our sum will have to terminate, and so from that we get rho naught equals 2n, where of course the little n is equal to the big N plus our L coefficient. So now we go back to the definitions we made a little while back, and we can invert these equations. So here's the energy in terms of this kappa, and then the kappa, if I take this here, I can express kappa squared like so. In terms of this rho naught. So if I go through and plug all of this in, we get the famous energy levels of hydrogen. And just rearrange this a little bit. And so those are the pieces there. I get 1 over this rho naught squared. And so if I clean this up a little bit, I get negative massive electron, 2h bar squared, and here's how people prefer to express this. And then again from rho naught, we get a factor of n squared, where I've already worked the 2 into there. And so this is our famous equation for the energy of the hydrogen atom, and it's quantized. And so what's going to happen is we're going to have different levels of solutions for this letter n as we go on up. And so this is where our energy equation comes from. So we go back and look at our equation for kappa. We have something along these lines here. Involving a rho naught. And of course, rho naught we're saying is 2 times our new quantum number. And so we can express this here we're going to just slip the 2 over here, and this is the n. And so we typically will write this as a group of constants that we'll call a. And these constants work out to be like this here, and this is will work out to be Bohr's radius. So this has units of length, and when you figure this out, you get 0.0529 times 10 to the negative 10th meters, which was the first radius that Bohr got with with his Bohr model of the atom. And more importantly for us, this is going to be how we're going to define this rho. So now at this point, it's just a matter of unpacking everything that we have. And so this kappa times r will be like r over a to the n. And okay, so our goal is to find this r function. The r function will be defined in terms of the u. And if you remember that u function, we had the two extreme, rho L plus 1, and then e to the negative rho, and then times our summation of polynomial terms. And we're going to go through now. So again, this thing is this guy here, and attempt to write this out and go through and solve or show how to solve for the radial wave functions. All right, so let's show how this works. And so what we're trying to do here is this top part. We're doing this. So we defined our n quantum number as n, which is the number of turns in our sum plus L. And again, if you remember, our sum is right here. This is our extra part of the solution, rho to the j. And so we're looking for a solution to our r radial function of this form right here. And so we can go through now and just look at the first couple of terms. So the first one will be n equals 1. That's the lowest we can have. So n equals to 1. If we put that in over here, by definition we have to have a term in there, so that would be 1. This implies that L has to be 0. So when n equals to 1, L has to be 0. And then what we do is, let's look at this sum here. So this sum, let's figure out the first one we want to do is j is equal to 0, which would lead us to c to the j plus 1 would be 1. We don't even care about the denominator, only the numerator. And so if I write this out, so 2 times j, which is 0, plus L, which is 0, plus 1, and then minus n, which is 1, times c0. So this top part equals 0. So c1 equals 0, and that implies that every other c greater than that will be 0 as well, because the way this works is the j plus 1 depends on the jth term. So this is a sum of just 1, and so our v of rho will just be the c0. So if I plug everything in here, let's see, the one last thing we got to remember is that our rho is r divided by a over n, which of course in this case n is equal to 1. And so what this gives us here is r over a, L is 0 to the 1 power, e to the negative r over a, and this piece is just our c0 piece. And so when we clean this all up, we get c0 over a, e to the negative r over a power. Now what we're going to want to do is we want to normalize this. And so if you remember, we separate out the normalization pieces. And so for us to normalize this, we're only interested in this part right here. And so we're looking at our r absolute square, r squared dr. And if you remember that the function we just got out of there was c naught over a to the e negative r divided by a. And so if I plug this in, I get 0 to infinity. Absolute square C naught squared over A squared e to the negative 2r over a r squared dr. And this particular integral here can be done. And so by looking it up in the back of the book or a table, and I get a divided by 4. Now we want that to equal 1, right? We want this whole thing to equal 1 in order for this thing to be properly normalized, which would, one way we can give us is C0 is equal to 2 over radical A. So this leads to a radial function that this looks like this when we put everything in together. 2 over radical A cubed e to the negative RA. Now, the particular spherical harmonic that we need for this one, if you remember, the spherical harmonics are set up so this is the L and the M. In our particular case here, we'll be looking at the y00, 0, which is 1 over radical 4 pi. So our total wave function, when we put everything here together, would be 1 over square root pi. And this, typically what we do is we will write out the n, l, m values here. So this would be 1, 0, 0. So here it is, the ground state of hydrogen we got building up from the radial function. Now, let's try to do this for the next state, which would be the n equals to 2. And so we'll do the exact same steps we did before. So here the quantum number lowercase n is equal to capital N plus L. And so this n now is 2. And so now this gives us a couple different options. We can either have n1 plus L1 to equal 2, or we're going to have n2 plus L equals 0. And so we notice here a trend that L here is equal to 0 or 1. And we're going to find this as we go forward. So whatever n is, L will in general go from 0, 1, 2 integers all the way up to n minus L. So we're going to find this through all the different pieces here. We also just a little bit of nomenclature. So generally these radial functions are specified by the n and the L. So here we have two possible choices. So this one here would be the R 2, 1. And this one here would be the R 2, 2. So just like before, we can take this formula here. And so now we can just break this down a little bit. So Cj plus 1, if I look at this top part, it'll be 2j. And so we're going to do this now for the case, actually this should be 2, 0. For this guy here, the R 2, 0. So we're saying that L is 0 and that N is 2, so negative 2. So it's j plus 0 plus 1 minus 2. So I get j minus 1 over top of the numerator now, which we do care about because we can see in this case here our capital N is 2. So we're going to have 2 terms in our sum here. And then downstairs here, this is just j plus 2 c to the j. And so we look at this. Let's do the first case when j is equal to 0. So it's c0 here. We're solving for c1. If I plug in a 0 there, I get negative 2 on top. And then downstairs I get 2. And so this works out to be negative c0. And then we see that if we plug into the next piece, I get c2 equals upstairs we get 2. And now for this case our sum is j is equal to 1. So I get 1 minus 1, which of course is equal to 0. And so all terms after c2 will be 0. So this implies that our polynomial looks something kind of like this. It's just going to be the first term c0, and then the second term would be c1 times rho, but of course here we see that c1 is negative c0. So this would be our sum there. And so if we look over here, our r to the 0, so it's the same sort of deal as before. So 1 over r over 2a to the L plus 1 Again, this is the case where L is equal to 0. We're doing this case right here. So this is again to the 1 power. E to the negative R over 2A, and then our sum is C0 minus C0 R over A. And so if I work through this a little bit, I guess I've been kind of like this. R over 2A, and then that would be C0 1 minus R over 2A. Again, we're using the definition here that rho is 1 over, R over A to the N. So just like before, we can normalize this. This is what our the first couple of these radial wave functions look like. Again, you would typically look this up in a table, but hopefully it's nice to be able to figure out where they came from a little bit. And these are our radial wave functions, which have the form R n sub L. And then what we're going to find is that we can write our total wave function as a combination of the R and L, and then our spherical harmonics that we've previously discussed. So now we're just going to basically move forward and show how to work with these things. So let's just recap a little bit of what we did. So starting with the radial function, we were able to find the energy of the hydrogen levels, which looks like right here. Again, this is probably the most important equation in quantum mechanics. And so we get E1 over n squared, where of course E1 is our famous negative 13.6 electron volts. And so where did this come from? Well, this came from first of all, so we have an n quantum number, which is an integer and is quantized. N tells you about L. So the way that it works is n is greater than or equal to L plus 1. Another way to put that is that our L values will go, starting at 0, will go up by integer values all the way to L minus 1. And what we're able to do, we're able to solve for our various radial wave functions.